I'm Keigo Nitadori, working at technical scientist as a technical scientist at RIKEN R-CCS, where the supercomputer Fugaku exists. This talk is mostly reuse of the RIKEN CEA workshop held at last December with a tiny update. So sorry for guys who are there repeating the same slides. Right, okay. Yeah. Good morning for United States. Good afternoon for Europe. Now it's just 0 a.m. JST. But please don't worry. Now our Fugaku is full node run project time. So I have a duty from 3 a.m. to 9 a.m. to watch the Fugaku nodes. So today I work in mostly American time. So abstract is that this is mostly my personal experience insights as a first time use of Kokkos. Maybe mostly supported from only the online material or official manual or YouTube lectures, but without any support of other Japanese or community support. And the target is a mini benchmark code of the Lattice QCD code developed in Japanese community, Bridge++. The kernel type is domain wall fermions. That means in user, Lattice QCD simulates on four-dimensional space-time or four-dimensional Euclidean or discretized coordinate. But spinol has the fifth dimension for chirality, what so-called gamma, also called gamma 5. So it's sort of state-of-the-art method, and we have one extra dimension on spin-offs that's very somewhat expensive but very accurate. One of them one of the target of the current or next generation supercomputers. In this porting, I only implemented mult kernel called mult. That is corresponds to matrix vector multiplication. Matrix is sparse but regular grid type. Vector and gauge field, and the vector part corresponds to the fermion or spin-off. So solver, not yet the CG solver itself, but this mult kernel is the most expensive time-consuming part in Lattice QCD simulation. Just for escapement, this is not the official statement of the Lattice QCD code developers or Kokkos developers, but my personal experience and what I felt during the development. The talk is organized in three sections. So the first one is Hello Kokkos, introduction to Kokkos, maybe to me. In the next section, I describe the code Bridge++ and supporting. Finally, I report the performance obtained and conclusions. The motivation, so why I started Kokkos is that in the background of the Japanese national flagship supercomputers in K or Fugaku, we did not employ any accelerator, and they are homogeneous CPU-only system. Of course, during the designing phase, some kind of sort of accelerator comes to be candidate, but most of the reason is that the ecosystem or compatibility of existing application code. That means if we put huge accelerators to increase the peak performance or performance by energy, users do not have much resource for the software development. But for the next system, we cannot escape from using accelerators. In Fugak Next, it's planned to operate in 2030 around that years. That will have some GPU. Can be NVIDIA or can be AMD. Now, prior to the operation and development and operation, we have to seek the software development platforms. So one candidate may be directive-based OpenACC, OpenMP with implicit data transfer. The other one is modern C++ library. Users are responsible for data transfer, and in most cases, users have to rewrite code entirely. But expected performance or flexibility to many architectures, it can be expected in unified source code tree. So what is Kokkos? Okay, this is my perspective. So I am just a user, not a developer, not evangelist. Modern C++ library can be either library or framework or even ecosystem for performance portability. So the performance portability is the most important keyword for Kokkos. For single source code tree, it's vendor neutral. We have many back ends for OpenMP for multi-core GPUs, CUDA for NVIDIA GPUs, and heap for AMD GPUs. Also, yeah, unified source code tree is very important in the sharing of the use of accelerators in Japanese HPC community. Most scientists say that they cannot manage a specific branch for specific architectural accelerators. They can only manage one source code tree. That means their Kokkos or directive-based approach can be candidate for such users. So, first insight of Kokkos is it's mostly for writing new code or rewriting existing code from scratch. We can make in some sense, do this for modifying existing C++ code, for example, or add some plugin to existing Fortran code, but in C++. But it does not look a natural way to do so in this framework. This is, requires explicit data transfer, unlike directive approaches. You don't have to be very deep C++ expert, but some knowledge, especially Lambda from C++ 11, is required. Also, what Lambda syntax is very simple and intuitive. What you have to care is capturing. So C++ Lambda has value capture and reference capture, and mostly Kokkos employs value capture by value. But if you capture STD vector, for example, it's very expensive copy. But if you write your data structure in Kokkos view, copy by capture, capture by value, cost is almost negligible. Because you just copy the pointer. So the first barrier I felt starting Kokkos is just hello world. That means you can write 10 lines of hello world in either CUDA or Kokkos. in CUDA, this is only for NVIDIA GPUs. And in CUDA toolchain, NVIDIA supports NVCC. Actually, it has complex of many tools. But for the user side, just you type nvcc hello.cu and then ./a.out, you get hello world or result of some CUDA APIs. In Kokkos, I tried to read the document introduction, but so finally I realized that starting Kokkos is starting to launch and understand CMake. So there's no wrapper Kokkos CC. So because Kokkos is designed to support multiple platforms unlike NVIDIA, NVCC. That means Kokkos needs to be coupled to some powerful building tool like CMake. Finally, I reached a workaround. It's that you to use the common.cmake file found in Kokkos tutorial. And this common.cmake was very nice and just include, so this is almost the minimum CMake file list.txt, and just you include common.cmake, then you can build either for CUDA or OpenMP in very small command. Also, the Kokkos source code tree is automatically downloaded when needed. Also, the Kokkos library for CUDA is built in the build CUDA directory, or in similar way, I make build OpenMP directory. Kokkos library for OpenMP is built in this directory at the same time. My claim at last December is now obsolete, and thanks to Damian, he made me a new version of quick start page. In that page, simplest example, without common.cmake, but cmake list text is shown. So maybe this is just headers, like include stdio, and effectively user need to write these two lines. And this is the system side. That means in this fetch context and fetch context make available, Kokkos source tree is downloaded. So this way is much simpler than the previous tutorial copying file from tutorial. So now it's very easy. Copy and paste these 1, 2, 3, 4, or 2, 3, 4, 6 lines, and just type cmake, blah, blah, blah. And for the actual build, you can call cmake -- build, but just you can call make. And after that, I also tried to install and compile Hello World with Spark. Spark is a famous package management system for HPC. I think it's very easy to use for users, or even if you don't install Kokkos in Spark, sometimes Supercomputer Center supports many open source libraries via Spark. So just ask the center to install Kokkos for example, for OpenMP or for NVIDIA GPUs installed in that center. So if I type spark find lx, I have 3 packages. GH is GitHub CLI. That's needed when I need to log in GitHub without SSH key. There are 2 Kokkos installed, and I did not show to save pages the detail of each package. If I type spark find minus LXV, many other options for build Kokkos is shown. So one of them is for Kokkos plus OpenMP. The other one is Kokkos plus CUDA. Now Kokkos is installed, and what users has to do is just like the very tiny CMake files.txt. And when Kokkos is loaded via Spark, just find package Kokkos required, then the CMake can find Kokkos. Also, what is nice is that how we go one version build OpenMP and the other version build CUDA. What is nice is that only when you type CMake minus B, adequate version of Kokkos is loaded. So at the first time, if you don't modify CMake file text, just load OpenMP version, make directory, then unload. Load CUDA version, make one directory, build directory, and unload. Then you update your source code, just type make in each directory. So these 2 pages are updated from last RIKEN CEA workshop. And then let's go to the application side, Bridge++ code. Bridge++ is a community Lattice QCD code mainly developed in Japanese community. The development started in 2009. And I thought it's intended for K computer, but at the same period, BlueGene Q is installed in KEK, that's the Japanese largest high energy physics center. So the initial version is intended to be used with BlueGene. Before that, each user wrote their own source code managed. But from BlueGene, you need to manage many MPI processes. From that period, the community needed the common community code managed by the code development experts. Recently, mostly 1 year from the release of version 2.0. In version 2.0, experimental accelerator branch in OpenACC and CUDA exists. My Kokkos branch, or just putting of one kernel benchmark, this is an unofficial one. So in the Lattice QCD, the fermion, or also called spinel or quark, that exists on the lattice point. So this is the view in 2D, but the grid point has 4-dimensional structure, and for each lattice point, the spinel has a fifth dimension. The matrix or part or gauge lives in the link part, and it's SU3, that's 3x3 complex and unitary, special unitary matrix. The marked part is that multiply matrix part, gauge, matrix, and vector spinel. That means spinel is here, and it hops multiplied by the gauge field and accumulated. So in 4-dimension, it's 8-point, or including the self, 9-point stencil computation. Next to the hello world in CMake, difficulty to me is connecting the 2 different worlds. That means, so I cannot totally rewrite the Bridge++ code. So I decided to make some module plugin that can be called from bridge plus plus code written in Kokkos. So inside bridge, not Kokkos view, but inside the bridge plus plus, it has similar data structure called field, sort of a flexible multidimensional array. And Kokkos side, all the data need to be stored in view. Also, so first I made a class kfield.hpp as an interface. Also, the bridge plus plus includes this header, also not as an executable binary, but as a dynamic link library plugin is served to bridge plus plus, and runtime the bridge kokkos.so is read and executed. The difficulty was the sparse connection of these two words. So kfield.hpp eventually has to contain Kokkos view. That means this, if bridge plus plus includes this class header, in naive writing, it also includes Kokkos core.hpp and Kokkos complex HPP. So in this way, bridge plus plus itself starts to depend on the Kokkos headers. That means entire bridge plus plus needed to be built in one CMake file. So in such situation, technique called p-impl idiom, that means in the interface, just hold the impl pointer to the implementation class. The detail of the private members are totally hidden to the upper layers. In textbook level, I knew such kind of technique, but this was the first time to me to write in this way. So it needed a careful design. And now we get into the data structure. So spinel, each spinel is a Dirac spinel. That means 1, 2, 3, 4 complex numbers exists. Also, this is a QCD. That means 3 colors exists. That means in total we have 12 complex number in one spinel, one colored spinel, or that means 24 spinels. For GPU, unlike AOS, that holds 24 real numbers in one structure, but SOA, that means each real numbers makes array and can be accessed in core list way. But in that way, we will have 24 strings that could be managed, but sometimes too many for efficient use of cache or so. So in this benchmark, my approach is pack 4 elements, too complex as 2 spinel, because the float 4 is the most natural data structure for GPUs. So these 2 elements forms an array or stream of float 4 data type. In this way, we can reduce number of strings from 24 to 6. So the data structure of view spin becomes like this. 2 spin holes are too complex and areas of float 4. And we have 1, 2, 3, 4 dimensional. And this is just the label. This is the volume. That means 4 dimensional volume is collapsed to 1 dimensional. But for even odd methods, we divide it by 2. And this 2 is the upper 2 spin and downer 2 spin. This 3 is for 3 colors, RGB. And NS, it's typically 8 or 10 or 12. This is the length of the 5th dimension. And for the gauge field, okay, spinner, express spinner in composition of 2 spinners, it's natural, but gauge is totally different data structure. It has, 3 times 3 complex numbers. The numerical structure is totally different from spin. So it's ugly, but for the gauge part, I assigned in this way. So pack the first and second row as 3 spinners. The last row, 1 spinner plus some remnant. That's because its special unitary matrix has a nature that we can, if we can ignore the last row can be reconstructed from the outer product, cross product of the first row and the second row. With extra flops requirement, we can reduce the memory access requirement. So that means gauge field can be expressed in 3 spinors in minimum. In optional, one spinner in the third row, and it wastes the last 1 element, but at most, without any reconstruction, we use 5 streams. In minimum 3 streams, optionally 1 more streams, or only three element is reconstructed, or without any reconstruction, we use 1, 2, 3, 4, 5 streams. So the data structure to spin becomes like this for the volume, but for even odd methods divided by 2. And 4 is for directions, spatial direction, X, Y, Z, D. And 5 for number of streams, and 2 for even or odd. And even odd decomposition look like this. So each lattice point has even indexed 1 or odd indexed ones. So gather even indexed ones to one array, other one, odd indexed one to the other array to store that. And mathematical level, we skip a vector spinor field to even and odd. And matrix is divided by 4. So even to odd potential axis, odd to even potential axis. Odd to even and even to odd. Also, diagonal term, self term exists. And in Lattice QCD simulation, diagonal term is not scalar, but in sparse matrix, its inverse is required. So by solving this, we can write like this. That means to solve X even, we repeat this operator. So even array, and by DOE, it's hopped to even field, odd field, and multiply inverse of self term, and vice versa. So this is the property of the target benchmark. So in this way, many kernels is generated. So I named these ones for stencil kernel, stream kernels. For the positive definite eigenvalues, last time D looked like this. Also, its dagger is need to multiply. That means so in D we have 2 stencil access pattern. Also in D dagger, the same ones. substantial kernel is spatial hopping for the spacetime, as known as the QCD kernel, well, without diagonal terms. And in this time, MPI, Halo exchange is not implemented, but it requires MPI exchange. And in this substantial kernel, some potential of reusability of data, sometimes explicitly or sometimes implicitly, because it's substantial access. Sometimes if we can use cache for data reusability. The other part is diagonal stream kernel. So just before and after stream kernel, or substantial kernel, stream kernel is called. So one by one, starting from stream kernel, one stream kernel, then substantial kernel comes. So in total, stream kernel is called 5 times. This is site local and element by element operation for the 5th dimension. But to the 5th dimension, it has tridiagonal matrices structure. So forward multiplication of tridiagonal matrices or its inverse is needed. Also, in this kernel, so this is element by element. That means no data reusability. So this kernel can be a good benchmark for the effective memory bandwidth benchmarks. So in 3 of them are one read, one write. That means read set of 5th dimensional spinel, maybe multiply diagonal matrix, its inverse, then store. But because of the 1 minus product structure, some kernel has 2 read, 1 write, or 2 read, 2 write stream access. This is not straightly related to how we write in Kokkos, but just write stream kernel in modern C++ for GPUs. So we have to treat array, but with NS, typical value of NS may be 8 or 10 or 12. So if we fix this for compile time constant, GPU's compiler has chance to put everything, all 8 elements here, to the register. The register pressure 16 is not very large for GPUs. So I hope these arrays can be stored to registers. Then we can eliminate extra memory access. But at old days, in Fortran 77 era, I think people modified this such integer parameter before you run. Just build it, just modify the parameters in the source code and just build it again, then submit. Because the job running time is much longer than the compilation time. But today, people do not like to do that, to fix such parameters at compile time. These files must be written in the configuration text file fixed at runtime. So in this, for that purpose, I made a preset template technique. That means if you write const express NS presets array in this time, I write 8, 10, 12. In this case, 3 different kernel is generated. So if you increase these numbers, the compilation times becomes longer and longer, and binary becomes larger. But the three different build is acceptable. In these 3 numbers, almost all practical simulation can be covered, except that using a very large NS to check convergence of chiral symmetry. And by using recursive template and terminate, if we write in this pattern, the compiler instantiate 3 patterns available, and finally it stops infinite recursion. This technique can be used even for CUDA or OpenACC version, but just it's my favorite in my development. Let me introduce such a little bit tricky but very useful technique. And finally, I report performance and conclusions. In GH200, at RIKEN R-CCS cloud, using 1 GPU, at the first shot, I observed a pretty good performance. So in combining total both kernel and flops count is the on-desk paper and pencil counting, and divided by timing, we get 6.7 teraflops. Peak is 67, 10% of the peak. But mostly Lattice QCD simulation is memory bound. So from comparing the byte per flops ratio, it's quite nice value expected from the machine spec. Also, in total 0.44 seconds for 32 cubed lattice point, we can split and we can make breakdown of the stencil kernel and stream kernel. And in the stream kernel, we have a theoretical memory access count. So this this bandwidth is calculated from the stream kernel part only. And it reports 2.4 terabyte per second. So, and the nominal peak of the GPU is 4 terabyte per second. That means we get, in application level, 60% of the peak memory bandwidth. And that's quite nice value. Also, the timing of stencil stream kernel is balanced. So that means both of them are well tuned and running at a reasonable performance. But if we go AMD, one good news is just I checked, it runs on NVIDIA GPU and just went to AMD environment and just just type CMake -D HIP something. In first shot, it ran. So that's very good news. But the performance obtained is rather poor in AMD environment. Now, currently, we are investigating the reason or how we can improve that. The performance obtained 0.8 teraflops for peak, 23 teraflops. Also, the bandwidth of the stream kernel is 0.3 terabyte per second for peak 1.6. That means to get 60% of the peak bandwidth, we need to triple the both flops and the effective bandwidth. I think maybe it's matter of the tiling or so, because in the kernel launch in Kokkos parallel 4, I set two-dimensional MD range. Kokkos assigns, but GPU has a grid, thread block and grid, double layered structure. Kokkos automatically assigns nice value. And I think in case of NVIDIA, GPU was nice or framework is nice, and we get reasonable performance by default. In AMD environment, we may need to tune that tiling by hand. So I gave AMD developers the source code. They can check the reproducibility of the performance or a bottleneck. So now conclusions, insights, and reflections. So to me, I had two challenges for new environment. CMake, that's all inevitable for Kokkos. That's the Kokkos, the native build system is CMake. Also P-Info. Usually I write code for myself, so do not need to connect existing two words. So P-input technique in the textbook, knowledge of the textbook was very useful, turned out to be very useful for this kind of project to make a plugin in Kokkos for existing code. And currently remaining problem, the largest one is the AMD performance. For the development or making this slide, I used ChatGPT 4. I feel that I am talking with human, and it knows, she make very well. It's measure tool. HIP, it knows not perfect, sometimes with hallucination, but it can answer HIP question. And CUDA is a measure tool used for long term, and the accuracy of CUDA answer is nice. Also, it knows Kokkos, and also, C++, many people are using. Knows C++ very well, better than me. For Kokkos or HIP, sometimes hallucination, but it can answer. So not perfect, but I enjoyed. Also, to ensure exact specification, we have to refer to the primary source, offshore manual. But without reverse lookup tool, we don't know which manual to read. But just I ask AI in just Japanese, it answers some name of API. Then I start to check offshore manual. That's the way of development cycle in ChatGPT. And especially in case measure tool like Python, but I have very little knowledge about Python, like Python or CMake, it's very helpful to, that's all. Just supplemental material, but it's time. So let's finish.
Yeah, thank you very much for this great feedback on the use of Kokkos, especially given it's nearly 1 in the morning in Japan.